Hello, calculus fans! Let's find the shortest distance from the point 3, negative 1, 2 to the plane 2x minus 3y plus z equals 5. Now first notice that that shortest distance is not 0. The point in question is not on the plane. If you were to plug in 3, negative 1, 2 into that equation, you would not get 5. So the distance from any point in space to the point 3, negative 1, 2 looks like this. The distance is the square root of x minus 3 squared plus y plus 1 squared plus z minus 2 squared. Now we want the point P to lie on the plane, so z should equal 5 minus 2x plus 3y. Now let's substitute that into this expression for the distance, and we'll get this. So basically what we've done is we've replaced this z with 5 minus 2x plus 3y and then simplified that expression. So now our distance is really just a function of two variables. Now I want to show you a very common trick that comes up a lot in these optimization problems. Notice that the expression that we were just dealing with for the distance had a square root in it, and those are kind of messy. So instead of minimizing d, we'll minimize a simpler looking expression. We'll minimize d squared. Essentially we just get rid of the square root. So if this is going to be a minimum value, then d will also be minimized. Let's compute partial derivatives. They look like this. So fx is 2 times x minus 3 minus 4 times 3 minus 2x plus 3y. We're using the chain rule and the power rule here. F sub y is equal to 2 times y plus 1 plus 6 times 3 minus 2x plus 3y. So now we have a system of two linear equations with two unknowns. And if we solve for x and y, we'll get 15 over 7 and 2 over 7 for x and y. I'm sparing you the details of the computation to solve this system of equations. You should make sure to carry out the computation to see that you get these values of x and y. Let's classify this critical point. First, we need the second partial derivatives, and they look like this. fxx is 10, fxy is negative 12, fyy is 20. That makes d equal to 56, which is positive. And since fxx is also positive, the second derivatives test tells us that f has a local minimum at 15 over 7, 2 over 7. Intuitively, we also know that this local minimum is actually an absolute minimum because there must be a point on the plane that is closest to 3, negative 1, 2. So if x equals 15 over 7 and y equals 2 over 7, then we can calculate what that distance is. Plug those values in for our expression for d, and we end up with the square root of 18 over 7. So our conclusion is that the shortest distance from 3 minus 1, 2 to the plane 2x minus 3y plus z equals 5 is square root of 18 over 7. Okay, that's all for now.